So far, we have discussed entropy, and we've also discussed enthalpy. Now, when we talk about those two different things, what those both of those lead to the idea of, will the reaction be, remember in our previous video, thermodynamically favorable or not, okay? In general, exothermic reactions tend to be more thermodynamically favorable. They're more likely to spontaneously occur than endothermic reactions. In terms of entropy, that same concept can be applied. Reactions that become more disordered, so reactions that have a positive delta S, tend to be more thermodynamically favorable than reactions that have a negative delta S. Okay? Now, when we put those two things together, notice that when I talked about the enthalpy and I talked about the entropy, they tend to be, okay? They tend to be more thermodynamically favorable, or they tend not to be. This equation right here is the ultimate equation that says, yes, it is thermodynamically favorable, or no, it is not thermodynamically favorable. Okay, let's look at the math here. So delta G, first of all, stands for Gibbs free energy. Okay, so when delta H is negative, so that's an exothermic reaction, and delta S is positive. Okay, notice you've got a negative value, and then you're going to subtract, and then temperature has to be positive, and in this case, entropy is positive. So you're taking a negative number, and you're subtracting a positive number, basically. Is there any way mathematically that number couldn't be negative? Of course not. So what does that tell you? It tells you that every time you have an exothermic reaction and the entropy is positive, it's becoming more disordered, it will always, again, without exception, always be thermodynamically favorable, because delta G will be negative, okay? So when delta G is negative, it's always, I'm just going to put T.F, thermodynamically favorable. Don't do that on the AP test. Okay, the opposite is also therefore must be true when delta G is positive. Well, when could delta G be positive? Well, if it's an endothermic reaction, and if it's becoming more ordered, then delta S is negative. And see, the double negative there makes that whole thing positive. So you're taking a positive number and you're adding another positive number to it. That, of course, must be a positive answer. And so when delta G is positive, it is never thermodynamically favorable. Okay? And again, those are the always and the never. Okay? So when delta H is negative, let's go back to my original one. When delta H is negative and delta S is positive, that, again, is an exothermic reaction that's becoming more random, more disordered. That's always going to be thermodynamically favorable because delta G is negative. Okay? When it's an endothermic process and it's becoming more ordered or less disordered, I like more ordered better, then delta G has to be positive, and it will never be thermodynamically favorable. Okay? Of course, the question's going to come up. What happens when delta H is negative, delta S is negative, and what happens when delta H is positive and delta S is positive? Okay, then there's that third component of this equation. So delta G equals delta H minus T. That is the temperature in, of course, Kelvin. Okay, so let's look at that scenario here. When they're both positive, so remember, let's go back here. Well, let's look at the table down here, because this kind of summarizes everything. When they're opposite signs, it's delta G is either always positive or it's always negative. It's when delta H and delta S have the same signs that we have to take into account the temperature. Okay, so, and again, they're not going to give you an exact temperature. Typically, they're just going to say low temperature and high temperature. Okay, in this case, when you have, let's say you have a low temperature, what that means is it means that delta H is the bigger factor here. And therefore, at a low temperature, delta H is the bigger factor, and therefore delta G is going to be positive. At a high temperature, again, we've still got positive and positive here. At a high temperature, remember, this whole negative T delta S component is negative. Okay, because that minus T delta S. So at a high temperature, now the negative T delta S plays the bigger factor, and therefore delta G will be negative. So it depends on the temperature. Okay, and that's what you see down here in the table, is when they're both positive at a low temperature. What you have to remember is at low temperature is that the delta H component plays the bigger factor. So whatever delta H is, that's what delta G is going to be. At the high temperature, the negative T delta S component is like what I like to think about it, and then that will cause that to be the bigger factor, and then it will be delta G will be negative at high temperatures. So please don't, I'm trying to teach this to you so you don't have to memorize this, so you just remember it. Okay, what happens when they're both negative, like right here? Well, again, anytime you're at low temperatures, delta H is the bigger factor. So if delta H is negative, then delta G is going to be negative. But then at higher temperatures, again, you've got the negative T delta S and you've got a negative delta S in there. That makes the negative T delta S become a positive, and then that becomes the bigger factor. So at low temperatures, delta H is the bigger factor, so it's going to be negative. But at high temperatures, the negative T delta S is going to play the bigger factor, and then therefore it will be positive. Okay. So again, it all comes back to, you can memorize that if you want, but it's much, much better if you can just learn the math behind this, okay? And again, they're not going to give you exact temperatures. They're not going to say, well, what about at 250? What about at 255? Okay, typically they say that it's going to be, it's either a low temperature, when again, at a low temperature, you forget about that part. Whatever delta H is, that's what delta G is. And at high temperatures, then of course you have to take that part into account, with again not forgetting that negative sign there. Okay, and of course that equation is given on the AP exam, and very, very useful in terms of determining, is it thermodynamically favorable or is it not? Okay, so this is a good table right here for you to come back to, yet at the same time, you can't use that on the real AP test. So, example 1. The following reaction occurs at 25 degrees Celsius. They give us the equation. They tell us that the enthalpy change is negative, and they tell us that the entropy is also negative. Now, without even looking here, without knowing this value right here, we can look, and we can go, oh, we're going from 3 gas particles to just 1 gas particle. Definitely we would, again, if we had to predict that, then yes, we would say absolutely delta S would be negative. So is the sign of entropy logical based on the reaction? Absolutely yes, because you're going from 3 gas particles to 1 gas particle. And you could add in there plus 2 liquids. Okay, and then you could even say which is more ordered. Okay, and then just stop. You don't need to summarize. You've said yes. No need to say anything more. Okay, now the next question. Is this reaction thermodynamically favorable at 25 degrees Celsius? Justify your answer with a calculation. So here, absolutely yes, we have to take that into consideration in terms of, okay, they're actually giving us a temperature. We have to calculate delta G. So delta G is going to equal delta H, which is negative 315 kilojoules per mole, minus T in temperature, in Kelvin, 298 Kelvin. Now here's where we have to be careful. Because entropy is typically a smaller value than enthalpy is, notice that entropy is typically given in joules per mole Kelvin. Okay, whereas delta H is almost always given in terms of kilojoules per mole. So when you put that entropy into this equation here, make sure that you convert that to Kelvin, to kilojoules per mole Kelvin. So I'm going to make that negative 1.250 kilojoules per mole Kelvin. Okay, and then notice those kelvins are going to cancel, and you're left with kilojoules per mole in both cases, which is fantastic. Okay, so I'm going to take negative 315 minus, and then I'm going to take 298 times negative 1.250, and I get an answer of delta G being a positive, and you don't have to put a positive sign, 57.5 kilojoules per mole. Okay, and so therefore, it is not thermodynamically favorable. Okay, not thermodynamically favorable there. Okay, now here's another question. At what temperature will the reaction become thermodynamically favorable? So here's the thinking part. The first couple are kind of just, yeah, can you put the numbers in? Can you solve the problem? Great. Now we actually have to think a little bit. Well, at what point does the reaction become thermodynamically favorable? Okay, and it's when delta G switches from being positive to negative, which we know is 0. So at what point will it become thermodynamically favorable is when we set delta G equal to 0. So we're going to say 0 equals, and now we're going to do the same thing. Negative 315 minus, there's our temperature, X, times, again, negative 1.250. I left the units out that time. We used them last time. It's fine. Okay, now to solve for X, the first thing I'm going to do is I'm going to move that 315 over to the other side. So 315 equals negative X times negative 1.250. And now I'm going to divide by negative 1.250. So 315 divided by negative 1.250 equals negative 252 equals negative X. Okay, and then obviously we're just going to divide by negative 1. So X would equal 252 Kelvin. Now, does that make sense? Does that answer make sense? We know that at 298 Kelvin, that it was not thermodynamically favorable. We know that when they're both negative, that at a low temperature, that delta H is going to play the bigger factor. So in this case, when do we switch from high temperature to low temperature is right at 252 Kelvin. Okay, so any temperature below 252, it's going to be thermodynamically favorable. Any temperature above 252, it's not going to be thermodynamically favorable. And what if it's exactly 252? Well, then delta G equals 0. Okay, and I believe that, yes, here in just a little bit, we are going to get into that a little bit more in our next video. But at that point, technically, it's not thermodynamically favorable in either direction, and we basically would say it's at equilibrium, okay, which, again, we're going to get into a little bit more detail here in our next video.